Hello and welcome to this video for Advanced Design System. And in about 15 minutes or so I'll show you how to use two separate ADS simulators for signal integrity analysis. Now the first one for either linear or nonlinear systems is the Transient-Convolution simulator. I'll give you an example with long transmission lines and high data rates where there are eye closure problems and bit errors, and I'll show you how to solve this, have a nice eye opening, and I'll be using a frequency domain model. And then for the channel simulator, which is only used with linear time invariant systems, I'll show you how to set that up and also tune with a couple of taps. It's a fast simulation and small data sets are the result. For transient, you save a lot of data, but not with the channel simulator. And for either one of these simulators, you can use the new ADS iProbe component that will give you a density plot. And for the channel simulation, there are specific sources you need to use. And with transient convolution, you want to use the time domain sources. So I'll show you all of that. And this is the density plot that results from the iProbe. It's basically an eye diagram. And here's our eye diagram, and you'll get that with transient convolution. And now let's run ADS, and I'll show you our first example using the transient convolution simulator. Here's our design with a long line and a high data rate, but let's begin now with the results when our impedance of the load and the source is not matched to our line. And to do that, let's look at the eye diagram. Here in the ADS data display, I'm starting with an eye diagram, and it shows a little bit of delay here at the crossing. You can see the bit error problems we're going to have, and this is not the type of eye that we want to see for our design. And if we look at a graphical representation of our transmission line, it's easy to see that when the impedance of the line, that is the characteristic impedance Z0, is not matched to our load, we get these discontinuities here, and our signal is going to be reflected back. Now sometimes you can have the source and the line match, so looking this way into the source and this way into the line, they have the same impedance. You're still going to get reflections if the load is not matched. And so the objective is to determine what's the correct or optimum value of source and load impedance that we need to correctly match to our line and remove or minimize the reflections. And the result will be what you see here, which again is taken from the example that I'm going to demonstrate, where we have a nice eye opening and we don't have any of those bit errors. Here in the ADS schematic, I've set up our long transmission line with a high data rate source, and I have the transient convolution simulator all set to run. Let me show you the details of this before we run the analysis and use the tuner to achieve our goals. Beginning with this transmission line and the substrate definition, I inserted both of them from the transmission line's multi-layer palette that you see here. Simply select the items and then insert them and set the values. This is basically FR4, so substrate 1 has a dielectric constant, a height, you can set the conductivity and so on. The line is 5 inches long and 10 mils wide. Here at this wire, I've labeled it using the name icon. It's a node name or wire label, Vout, so we can look at the bits if we want to. Now for our source. This pseudo-random bit sequence voltage source is a time domain source, and you can see here the high and low values, 0 to 1 volt, and the output impedance is done with a variable, RS. Also our load resistor is RL, also a variable, and I've set those impedance variables right here, so the source and the load have the same value equal to Z0, which I've set to 25 ohms. The rest of the variables, the timing variables here, are used for the source and the simulation controller. So let's begin with the data rate. That's 1 gigabit per second, and that's passed into our source here. Bit rate equals data rate, 1 gigabit per second. Then the rise and fall time for this raised cosine filter type of transition, which we've also set, is another variable. Now to get the rise and fall time, I've set up t bit, the time for our bit, so we take 1 over our data rate and then divide by 10, and that gives us the rise and fall time. That takes care of our source. And finally, our transient convolution simulator, which is inserted from the transient palette, And if you edit this controller, you'll see that it has a convolution tab set to auto by default, and all you have to do then is set the correct times. And I've already done that with variables. So the stop time is how long we're going to run the simulation by taking our value of t bit and using some multiple like 50 or 100 or 200 and so on. You can set the stop time from 0 to when it ends. Max time step here is actually the sample rate, and I'm calling that t step. That's what you see here. So if we think about the rise and the fall time, we simply take that variable, divide it by 10, and that's enough sample rate, fast enough to accurately capture our rise and fall time for our bits. And finally, I want to save this variable in case I want to use it in the data display. And so now we can run the tuner for this simulation. We have the data display window close by, so if you simply click on the icon, you'll see the Tune Parameters dialog appear, waiting for you to select the parameter that you want. And in this case, we're tuning our value of impedance. And the first thing I'm going to do is set the max value to 100 and the minimum to 0 with a step size of 2 ohms. Let's plug in a value of 50 because that's reasonable, and we'll see the results update in our data display. And here they are, and the eye diagram looks much better now. However, we can fine-tune it by stepping through the values, and now you can see we have an even better eye diagram. No more bit errors, a nice opening. And we can also look at the output bits, Vout, and that's from this wire label or node name here. Now to create the eye diagram, you simply insert a rectangular plot of Vout, and then you can place your cursor right here on the label and use the function front panel underscore I, and then the argument in parentheses is the Vout data separated by a comma, and then your data rate, 1e to the 9. And that's how easy it is to plot the eye diagram. And the other way is to insert an equation and then plot the equation. In this case, again, front panel underscore I, using the Vout data, and then a couple of arguments to center the eye. And you can easily look these up when you insert an equation by going to the functions help, and then you look up that function, and all of the arguments are shown here. For example, Vout is our data, there's our symbol rate, the cycles, and any delay that you want to center the eye. And that's how I created the eye diagrams for this example. And if we update the schematic and then close the tuner, the optimum value of source and load impedance is now set, and we can save the design, and that accomplishes our objective by eliminating reflections on the line, and the result is our nice eye diagram and the bit errors removed. And that's using our transient convolution simulator and our frequency domain model. And now, before we move on to channel simulation, I want to show you 3 quick examples. The first is our same single-ended line, but using an eye probe instead of collecting all the data at the node, and this results in a density plot. And then the differential line and an S parameter file, both used with ADS transient convolution.